In this video, we are going to talk about everything you need to know about graphs of exponential and logarithmic functions. Let's look at the basic shapes of exponential function first. So the shape is kind of the same, but the appearance of the graph will depend on the base. So if base is greater than 1, such as 2, for instance, versus base is less than 1, of course, it should be more than 0, so we need to add this, otherwise we can go all the way to negative if we just say this. So for base less than 1, such as 1/2 to the x. You know the graphs. Let's super quickly review. So 0, if we raise everything to the 0 power, we'll have 1. 2 to the first power is 2. 2 to the second power is 4, and so on. So basically you double every time you go by 1. And if you go backwards, you take a half of it. This is your negative degrees. So this is your shape. Okay. When you raise 1/2 to power of x, 0's degree is always 1 again. But then as you keep multiplying by 1/2, your value of y gets twice as low, and when you go backwards to negative degrees, that's when your numbers become bigger, double backwards. Why is this happening? So you see that the graph is reflection of the first graph with respect to the y-axis. And why is this happening? Because 1/2 to the x power can be written as 2 to the negative x power. In other words, whatever happens for positive x's here happens for the opposites over here. Okay, graphing logarithmic function on its own is not very easy. So instead, we are going to use the idea that logarithm is the inverse function of exponential function with the same base. So let's visualize the line y equals x. And I'm not going to draw it here. I don't want to mess up the graph, but if you reflect the graph, it will look something like that. So I'm going to draw it here. We will graph another logarithm function a little later more accurately, but for now, you just want to see the shape. So once again, visualize like exponential function got reflected over here. So the point that was 0, 1 now is 1, 0. The asymptote, the horizontal asymptote of the exponential function, which is the x-axis, now becomes a vertical asymptote for the logarithmic function, because x becomes y, as you remember, for inverse functions. Same thing happens for base less than 1. So this reflection is a little trickier. It will look something like this. And I'm going to draw it here. And I'm going to erase this one so it doesn't mess up my exponential graph. Okay, so same way as for base greater than 0, this point is 0, 1. So the corresponding point is 1, 0. And again, the horizontal asymptote here, the graph approaches to it. It becomes the vertical asymptote here, and again, the graph approaches to it, never crossing it, which relates to which calls for question. So what is the main and range of these functions? So from the definition of the function or from the graph, we can say that the main of exponential function is all real numbers. All real. You can raise a number to any power, positive number, of course. The range, though, is only positive, because when you raise positive number to any power, you will never get negative, you will never get 0. As you know, even without the graph, for the inverse function, the main and range switch. So let's write it and then we will look. X should be greater than 0 only, and range can be all real. Okay, so let's look at the graph. The main of logarithmic function, only positive, never On the left, never crossing the y-axis for both base greater and smaller than 1. And the range can be anything from negative infinity to positive infinity. Okay. Most important, maybe, exponential and logarithmic functions have base e. E, as you know, hopefully, is approximately 2.718, but it doesn't matter. So it's a number between 2 and 3. So when you need to sketch the graph, you just do it just with any other base, 2 or 3, just draw it, and you say the y-intercept is 1, and you're done. If you need more details, of course, you may need use a calculator, but essentially it's just another exponential growth function. Now, to graph logarithmic function, just like others, it's not easy, so I prefer just to use the reflection. Draw the line y equals x and reflect. Instead of 0, 1, we have 1, 0. The graph does not intersect the y-axis, and this is my graph of logarithm. I don't use exact scale, so I cannot check if that is exactly base 2.7, but that's how it looks, more or less. Let's look at one more example of graphing logarithmic function. What do we do if we really need to graph it, not just sketch? Let's pick some ugly base, like base 1/3. I have no idea how to graph logarithm to the base 1/3. I can sketch it, maybe, but if I need to graph, I will need to make a table of values. So I'm going to make a table, but I'm going to cheat. I'm not going to graph. I'm not going to make a table for values of logarithm. It's really not easy to figure out which values of x you want to plug in. It's not 0, 1, 2, 3 as we usually do. Instead, I'm going to make a table for the inverse function, which is exponential with a base, guess, yep, 1/3. So this is what I'm making table for. And this is easy. I would like to take a couple negative values and a couple positive values. So I'm just raising 1/3. I'll start with 0. 1/3 to the 0 power is 1. 1/3 to the first power is 1/3. Square is 1/9. Now I will have all reciprocals. -1 means it's reciprocal to 1/3, which is 3. And -2, it's reciprocal to 1/3 squared, so that will be 9. I'm not going to graph this one. I'm going to just say, okay, if this is my exponential function, then this is my logarithmic function. Y equals logarithm to the base 1/3. So this will be my x, this will be my y. Remember, the main of the exponential function becomes the range now, and the range of exponential function becomes my domain. So these are the x values I'm going to use. I'm actually going to highlight them so I don't lose them, don't mix them up. Okay, so I'm graphing it. I looked at my domain, I realized that it goes up to 9 and only positive. So that's how I set up my coordinate system. No negatives here, little long x-axis. So these are the numbers I need. When x is 9, y is -2. When x is 3, x is negative, y is -1. When x is 1, this is my x-intercept. Now, when x is 1/3, my y is 1, and I know I cannot show 1/9, so I just go that it gets higher and higher and will never touch the y-axis. So now I can connect them. Hopefully I can. Something like that. All right. Okay, let's see now how transformations change graphs of exponential and later logarithmic functions. Let's look at these two transformations of the graph 2 to the x. So the basic 2 to the x graph, let's draw it. We know the y-intercept is 1. We don't know any specific point. I mean, it's not hard to figure out. Maybe we should look at one point. Let's say this point will be 1, 2. This is the original 2 to the x graph. Okay, now we know what this transformation does. When you subtract 3 from the x, the graph is going in the x direction horizontally, and because we're subtracting 3, it moves to the right. So from the only point that we have, we count 1, 2, 3 to the right. And we are trying to graph a curve parallel to the one we have. Please notice, vertically it's not moving anywhere, so it will still have the x-axis as the asymptote. Let's look at this point a little more closely. So if you move 3 units to the right, then this is 3 comma 1. Let's check what happens. When x is 3, you plug it in. 3 minus 3 is 0, 2 to the 0 is 1. So yeah, it doesn't hurt to check with 1 or 2 points. Okay, let's look at the other graph now. 2 to the x minus 3. So here we're subtracting 3 from the function 2 to the x. So we are changing the y coordinate. Therefore, it will be a vertical transformation, 3 units down. So from 1 we count 1, 2, 3. So instead of 1, we'll have a y-intercept at negative 2. And we are going to try to draw the graph like sliding vertically. Every point of it 3 units down. Now, this is a little tricky because I want to make sure that the line, the original asymptote, remains an asymptote. So I'm going to draw a new asymptote now, which goes from 0 level to minus 3 level, 3 units down. So this is my new asymptote. It's kind of like graph is traveling with its own asymptote. So it still crosses the y-axis 1 point above this asymptote. So the x-axis kind of slides down with the graph. So this is my vertical transformation. I need to label everything. This is 2 to the x minus 3. This is 2 to the x minus 3. And this is 2 to the x. And maybe it will be nice if I draw these arrows here to show that every point travels 3 units to the right. Okay, so this is transformations of exponential function. Okay, now we will look at one logarithmic transformation only. We are going to start with the basic logarithm graph to the base 2. So the x-intercept is always 1. Yeah, if I forgot, I can graph 2 to the x. I don't want it now. And then I'm going to reflect it. So this is basic logarithm graph to the base 2. Okay. Now I'm going to translate this graph 3 units to the right, just like the other graph. So instead of 1, it will go 2, 3, 4. So all my points will go 3 units to the right. Before I draw it, I just want to make sure that my asymptote, which is an important like boundary for the graph, travels with the graph. It also goes 2 units to the right, so it will now be at the 3 level. So this is my new axis, and this is my graph, which goes on and on there. And I should label this 3. So this is it. And one important thing that I need to stress. Let's look at domain and range of this new function, logarithm x minus 3. Domain. Basic logarithm graph, whatever the base is, always domain is x greater than 0. But in my case, it's x minus 3. So I need to require that x minus 3 is greater than 0. In other words, x is greater than 3. This will be my domain. Look at the graph now. It totally makes sense because we are shifting the entire graph, including the y-axis, 3 units to the right. So this is my new boundary, and you can tell that the entire graph is to the right of it. So this is my domain, x greater than 3. And the range didn't change really because we shifted horizontally. Okay, so far in all my examples, we had nice numbers. 2, 1/3. So in real world, the exponential processes don't usually come with such nice numbers. So let's say you put $375 somewhere invested and your annual percentage rate is 7.2%. When will this amount reach $1,000? So let's set an equation first. So the function p of x 375. Okay, why don't you write the equation first and then come back, pause, and then after you write it, come back and check. All right, so what you wrote is probably, hopefully, I don't need $sign, 375 initial amount, then 7% a year means you're multiplying 1.072 raised to the x power. Okay, so if you just need to sketch the graph, that's not a problem. You don't need to do it to scale. You know that 375 is the initial amount. When x is 0, the moment now, p of 0 is 375, because anything to the 0 power is 1. So this is your initial amount, 375, and then it just grows. Okay, 7% a year. So let's say if this is 1 year, the amount goes just a little bit up by 7%. But I'm not going to do it to scale. I'll just draw some exponential curve, not very too steep. Okay, so you are going to learn how to solve this equation, how to solve problems like this analytically without graphs. So basically, the equation will look like this. When is this amount, 375 times 1072 to the x power, will reach 1000? That's what you want to find. And we will learn how to solve it without graphing. But if you have a graph, it might be even easier to do it if you have a calculator, of course. So we want to do it the following way. So you type in your equation, y1 equals this function, 375, 1072 raised to the x power. And then you may trace and see when it reaches, like trace, and see when it's 1000. But a much more reliable way would be to graph another function, which is y equals to 1000. So 1000 will be somewhere around here. And you're going to have this line, y equals 1000. And you're going to see where my graph, my exponential curve, reaches that level. You want to find the x value. What is the x for that? That's what the problem asks. So the sketch helps visualize it, but you really need to graph it with a calculator. So when you type your equations, y1 and y2 on the calculator, what zoom should you use to see what's happening? Because you visualize this diagram on paper, you know now how you can set up your window, more or less. So let's start with the y. So the minimum y, it could be a little less than 375, doesn't matter, maybe let's make it 300. And the maximum, don't make it 1000, you really want to see 1000, so make it 100 or something. Now, x, we want to start with 0 probably, and then how far do we go? I have no idea, so I really don't. It's not such a fast growth, 7% a year, so it may take a while. So I'll try 10. So when I did this, I saw a graph like this. You may try it and you will see something like that. So they didn't meet yet, but it looks like it's getting close. So I'll try 20, and then I will actually see what I need to see. I will see the intersection. And you can play around with a window. It's usually more beneficial than using zoom fit, because this zoom, the calculator doesn't really know what you need. And you know what to expect. This is why such a sketch can be very helpful. And then, rather than tracing to find this intersection, I would recommend to use intersect feature in calc, menu. which I hope you know. If not, please ask. I'm not talking about this in this video. Okay.